Okay, these are some more problems from section 4.2. This is number 16. And first of all, we just want to find any relative extrema and then intervals in which it's increasing or decreasing. So if we look at our function, first of all, we'll take the derivative g prime of x. This is pretty easy, 2x minus 1. And to check for relative extrema, we're going to find the critical numbers, and we'll find the values of x to give us the critical points. It can be 0 when x is 1/2. It's not going to be undefined because it's just a straight line. It's defined for all the numbers. So we draw our first derivative test. We'll draw our derivative here, and this is our critical value x. And we look over here, and we can see that the derivative, if I put negative, if I put 0 in here, which is to the left of 1/2, I get negative, and if I put 1 in here, which is to the right of 1/2, I get positive. So you can see the derivative is negative, the derivative is positive, so I do have a extrema there. Looks like a relative minimum. And then we can find out the actual value of the point by putting the 1/2 back in the original function. 1/2 squared minus 1/2 minus 12, and that equals negative 49. Okay? So this is what we have, and so my point 1/2 negative 49 fourths. Okay? And this is negative 49 fourths is a relative minimum because g prime of x changes from negative to positive there. And then again, the derivative is negative, so the function is decreasing. So since g prime, well, they wanted b was where is it increasing? So I should where is it increasing? So when the derivative is positive, the function is increasing. So since g prime of x is positive on the interval 1/2 to infinity, g of x is increasing on 1/2 infinity. We use closed interval when it's defined, of course. And since g prime of x is less than 0 on negative infinity to 1/2, we say g of x. The function is decreasing on the interval negative infinity to 1/2 inclusive. All right. So that was pretty straightforward. And then number 18. Here's number 18. Now this is a little tricky because because of the issue is we do have a point on this function here. If you look at this function, let me get this a little bit higher here. If we look at our function here, we do have a point where it's undefined because we can't have 0 in the denominator. So actually the domain of the function is understood to be negative infinity to 0 and 0 to infinity, so we don't include 0. So we would take the derivative. I would put this negative 2. I would write this as the 1 over x to the second power as x to the negative 2. Then I would just use the power rule. So that's going to be negative 2 times x to the negative 3. Then put that x to the negative 3 on the bottom. And it's going to be equal to 0 when the top is 0. Well, that's not going to happen. So it's not going to be equal to 0. It's going to be undefined when the bottom is 0. X equals 0. All right. But that's not in the domain. All right. So even if I did try to put 0 in here, I wouldn't have a value. I couldn't find a value for a point. So there is no relative extrema there because there is no value for the point because the value does not exist because it's not in the domain. So I can put this in here. It's not going to make any difference. So there is no critical. The critical point must be in the domain. So this isn't a critical point. It's just a kind of juncture point here. And probably just should have just left it like that because it's sort of strange because we do have changes of signs to the left and right of 0, but we don't have, that's not in the domain, so it's kind of like a black hole there, so to speak. Okay, so there are no extrema because it has to be a critical point. That means in order for it to be a point, it has to have an x value and a y value. It's not defined. That y value is not, there's no y value. The function at 0 is not defined. So we don't have an extrema. But we do have intervals in which it's increasing. And again, since the derivative is greater than 0 from negative infinity to 0, we would say k is increasing on this interval from negative infinity to 0. In this case, it would not be open. I'm sorry, it would not be closed. It would have to be open because 0 is not the actual point. 0 is not in the domain. So in this case, when we talk about the increasing, it would have to be increasing on the open interval. And then again, since the derivative is less than 0 on 0 to infinity, we'd say the function is decreasing on 0 to infinity. again, open at 0, because the derivative is negative, so decreasing, increasing. Okay? So that makes sense for you.